All right, good afternoon. So next session again is in the vein of performance tools a little bit, given that we're consuming some of the outputs or planning to consume some of the outputs. And the topic today is a bit of an introspection on how to use one of the big benefits of RISC-V, that is that we have an extensible instruction set and can add new instructions pretty quickly in order to address workloads. So the question is how to best co-evolve the RISC-V ISA in order to address application-specific workloads or benchmarks and close the gaps to other architectures or even leapfrog them. So this is a slide I usually have in pretty much any talk I give about RISC-V, just to set the stage and connect back to why we're doing this. So we have a unique selling point to many of the adopters, which is the fact that we are extensible, we are modular, and we have a complete tool flow to support this. So the modular ISA allows us to pull in whatever we need, shrink cores down, while the extensibility gives us the ability to actually address specific application needs or add in instructions either as vendor-defined or as future standard extensions. And all of that is supported throughout the flow by the development tools, by the emulators that we have. So we have an extension framework in QEMU, we have one in SPEC. It's pretty easy to specify what you want to run if you define a new extension. And we have the same frameworks in LLVM and GCC to add those things quickly, and there's plenty of examples to look at. So out of that framework, the question is how do we best use this in order to get gains for real-world applications. And for real-world applications, I also define benchmarks as those because most of those should be derived from real-world applications. So as of today, most of the extensions that are under fast track are actually derived from software needs. So in other words, our software groups have identified gaps, have identified optimization potentials that we're using and that we can use in order to define new instructions. So the list of these fast tracks is pretty long at this point. So it's most of the additional floating point instructions have really been identified by running floating point benchmarks. ZAWRS is coming out of observing multi-core workloads and comparing those to other architectures. And of course, one of my favorites, the conditional operations, is coming out of benchmark workloads and trying to optimize the number of branches and at the same time reduce the number of instructions in total, so improve our cache performance. But with all of that, we do have one basic issue that we need to address. So Donald Knuth already said, premature optimization is the root of all evil in programming. And some of that is really true on RISC-V today. So we are defining, or in the past, we have been defining new instructions, new extensions, without putting down a very clear use case for that and a very clear quantitative framework. Based on that experience, what we've been doing over the last year, it hasn't been happening in a single group. So all of the software group is involved with that. The toolchain SIG, PSABI, so all of the software groups you're going to see some efforts in order to do a more controlled evolution and one that is really fact-based and that is driven out of the needs of actual application workloads. So when we look at the big picture, and I have a bit of data later on, but we can keep that out of this presentation because it's really about the concepts that are critical. So when we look at how we want to evolve the RISC-V instruction set, and I think it's without question that we want to evolve it quickly, because at this stage, anything that we can get in, anything that we can do to address these workloads, it's going to benefit us before we have that large body of pre-compiled work out there that makes it hard to add new optimizations into. So as we try to quickly evolve, we have 3 different layers that we can address. The bottommost is the easiest. We just improve our code generation. So yes, RISC-V is less mature than some other architectures when it comes to code quality, when it comes to our compilers. But that doesn't mean that this is going to close all of the performance gaps. This also doesn't mean that we can leapfrog other architectures. So we will have some work to do in order to fully implement the right optimizations to address specific peculiarities of our ISA, like the lack of a 32-bit minimum maximum instruction. But that said, this is not going to be where we are going to leapfrog the competition and where we're going to really beat the benchmarks and make RISC-V the ISA for all of these emerging applications. Instead, we'll have to focus on the two higher layers of that, which is going to be microarchitectural and architectural. Now, both of them do have their own pitfalls. So it's kind of easy to add new microarchitectural suggestions. So we can come up with a list of very commonly used patterns. Just write down all of the idioms that the compilers are going to frequently generate and suggest that people implement fusion patterns for that. However, that is still going to be a large body of code, and we can't ensure that everybody is going to use exactly that pattern. So next just-in-time compiler comes along, we're going to miss this again. So we will have to address the architectural level as well and identify where we're actually missing ISA instructions, where there's new opportunities. CFA has added new rounding instructions. CFA has added a load floating point immediate instruction, because those were not easily expressible otherwise. And each one of these three layers of optimization is coming with its own set of difficulties or its own set of pitfalls. So if we're adding more architectural instructions, there's an obvious cost associated with it. We have limited opcode space. In fact, when looking at our opcode space, it is sometimes scary how few major opcodes or instructions we have and how full our opcode space in 32 bits already is. So we're limited in how much we can still do in terms of adding ISA instructions or new instructions without going into the 64-bit space. So we need to justify each of these instructions very well. And we have to make sure we don't add things that eat up a huge swath of our opcode space. And then we turn around 2 years from now and decide, well, that was a good idea in principle. But when we look at the details, it really doesn't give us much. Or even worse, it's so specific that you can only use it in assembly and can't even map your higher languages to it. Secondly, this always comes with an increase in complexity. So every time we're adding new ISA instructions, it has to be a well-thought-out process. It has to be driven by actual data and an expected benefit for typical applications. Because otherwise, we're going to end up having all that support, all those additional optional extensions that are going to complicate our compilers, that are going to, I mean, the biggest problem is really our test metrics at this point. If we look at it without profiles, profiles are going to make everything easier there, but if we look at it just raw as RISC-V without the profiles, we're having a large number of different combinations that we can test for and support already. Similarly, as I mentioned before, microarchitecture has its own pitfalls. So you compile from one microarchitecture, you move it to another one, and your benefit is gone. So the more we give hints to implementers on that side, the more we're starting to limit the innovation they can do or make the implementation effort more complex. And finally, as I said before, code generation, great if we do it. We'll end up on some corner cases where we didn't do things in the ISA that would have been easy and make the compiler carry the entire burden and really do the heavy lifting and have lots of code or lots of optimization phases for that. So what we really need in order to drive this is real fact-based decisions. So quantitative analysis of the actual workloads, of the dynamic behavior, as well as workload characterization, understanding what each of the workloads does. As of today, within RISC-V, we haven't really built up that database of workload knowledge. So the performance modeling group is actually looking at how to do that with the traces. And part of their charter is to come up with a way how we can build up those characteristic profiles in order to make the work of optimizing and taking the optimization decisions easier later on. So how does this process of driving this based on facts really look? So everything is involved in this. So first of all, the evolutionary driver is really the workload. We need to decide what workloads we can pull in. On the software side, in the software HC, we now have a number of special interest groups that are focused on different aspects of the overall software ecosystem. So we have AI, we have machine learning, we have graphics. There's a number of groups that are more on the database and server side today. And what we hope is that we actually bring in a standard list of benchmarks or representative workloads from each of these groups. That means we need to augment our standard benchmarks with real-world workloads that are known and understood within RISC-V. It's something that the toolchains group is involved in. It's all the 6. I can, just as before, only ask to join these groups and help build up that knowledge, because this is what's driving the entire process. Because we're taking that data, or we're taking these workloads, and we're pushing them along the pipeline into our emulators. Again, you've heard the question before, what is the status of the simulator group? Where and which ones of the groups are, or which ones of the simulators are we using in order to get data, actual runtime profiles, traces out of that, do the counting of instructions, identify the hot blocks, look at where there's missed opportunities or frequently recurring patterns. This is something that a number of the member organizations are doing today, and that we need to lift up to a higher level within the toolchain SIG and within other groups in order to have a clear plan on the future optimization to take and the future strategy. Again, this is about sharing information and ensuring that we're using the same process and make the data available in a reproducible way. And at the heart of all of this is really, we're taking these benchmarks, we're putting them through the tool chains. The tool chains are constantly evolving. There's work being done by a number of member organizations upstream. So your compiler from a year ago is not going to match the compiler of today. I just found out a couple days ago that, in fact, LLVM now supports linker relaxation on RISC-V, which it didn't do a few weeks ago, and that this is on main. So one of the challenges is we are really constantly evolving. We need to refresh this data that we have, and we need to do that on a community scale instead of doing it within the individual member companies and share the knowledge. And we need to put it, after compiling it, through those emulators to see how it performs and at different profiles of our architecture. Turn ZBA on or off, you will see an entirely different behavior. Out of that, we get standardized performance metrics, hopefully standardized at some point, and feed that back into the proposals. So this is the process that we're using on fast tracks today. This is the process that we've been prototyping in a way on ZFA, on ZCont, but that isn't thoroughly being done throughout all of the new extensions and throughout the entire ecosystem yet. However, what this really tells is we need to look at the entire software ecosystem together with the micro-architects and the architects. So this diagram basically says we need the architect support, we need the micro-architect support, we need performance tool support, and we need the toolchain developer support before we can do fact-based development for any new extensions. Now, to highlight why this is so important, let's just take 2 examples from our past. These examples have come up in the toolchain SIG at different stages of the last year. So CBS, single bit instructions. We have them. They are generally a good idea because they allow us to efficiently set and clear bits and do some of these workloads where we're just tagging things. Perl bench in SPEC is a very good example of where this is being done. Even GCC does it internally a lot. However, it only replaces 2 instructions on average. So our own rules would have said, well, maybe let's think about whether we need them and whether we need them as immediate and non-immediates, because it's opcode space. And much worse than that, the C language standard says that if you shift something, an unsigned value, out of the space, it's taking modulo the width. These instructions are actually taking modulo on the shift amount. So if you're trying to set bit 65, you're in fact actually operating on one of your bits, both on the 32-bit and on the 64-bit space. So this is leading to the problem that this is going to be used less in actual code, in actually generated code, than was originally expected. And the weakness of the process at that time, so this was 2 years ago when it completed, was that we did not do the full feedback loop. A proposal was arrived at by saying, well, this might be good for one application, or we've seen that on a different architecture, and we didn't do the full validation. We didn't gather all the data. We didn't have the compiler ready. We didn't run the big benchmarks on the emulators in order to see what happens if we change the behavior of the instruction in that aspect. I mentioned it before. We don't have 32-bit minimum and maximum instructions. It's great fun because sometimes you can't use them. So that's CBS. Although minimum maximum is actually a CBB instruction, but I didn't have enough space in the lower box. So CBB is equally fun. So there's one instruction in there that is a very good example of what we would have done differently had we done the full cycle, which is ORC-B. This instruction, as it was originally intended, is really only used for string compares, or for determining when a byte contains a null character, so string length, string compare, any of those. We even have an example in the back of the bitmap specification where we're giving sample code for each of these. The interesting thing is that it is always followed by a compare against -1. So we're always wasting a register on holding the -1, or we're doing a negate before doing the compare, just because we didn't change the spec a bit. And every microarchitect you're talking to is going to tell you, well, if we already do that expensive ORC-B, we could have also negated the result. So in other words, what we did in the past is close to optimal, but not optimal, because we've been missing that important feedback loop. So let's look at 2 recent case studies. So some of that, actually most of that, is on our public mailing lists to follow up on. ZCon is currently, I think, in review. CFA is also going into review. So these were very strongly based on quantitative analysis. We have new rounding instructions. Interestingly, some that ARM already had in CFA. So this is more like a bit of confirmation bias. So we do the analysis, we see what we need, and if somebody else has it, we at least know why they have it. Not doing it the other way around and just saying, hey, I'm jealous, they have this instruction, let's pull it in, and then we can't figure out how to make good use of it. So this is completely done on Imagic. Floor and seal show up with about 9-point-something% in total. Depending on where the branch falls on a specific compiled run, you will see a speed up by 9 to 19% based on that. And that can be done very quickly, immediately, and drives the decision. And the output is really just a few minor opcodes in this case. So you're giving up about 16 code points or something like that, and get an 18% speed up. The other aspect of this is really going into the load FP immediate. This is another big topic that's coming out of CFA. And we actually have a very small load FP immediate. One that has very few bits in order to load those immediates, based on looking at large quantities of code, because it turns out people don't really want to load random immediates into their floating point registers. It's, okay, we can do a 0 quickly, but it's 1, 2. It was about 10 in total, but that was a large quantity of code. And you can quickly encode those in about 5 bits. So minimum amount of code space used for the maximum benefit. And anything else needs to be done eventually once we have a quick way to do 64-bit loads. The other big one here was ZCondOps. So ZCondOps is actually interesting because it's all coming out of Ventana. They completely prototyped it. And we helped prototyping it there. So it has actually been proven in terms of all the numbers for a year before this was bubbling up to a standardization effort. And it looks like a small extension because it follows the RISC-V philosophy, 1 output operand, 2 input operands. But if you look at the full analysis, it's saving usually about 2 instructions on your typical branchless sequence, which you can always synthesize. And looking at the frequency of that, you will see there's 1% of instructions gone on non-obvious benchmarks like Perl bench, just because you're optimizing these sequences that the compiler is frequently going to emit. And there's a very interesting side effect on that one, and that is if you take the quantitative analysis one step further and don't just look at how often does it occur, how much savings does it provide, the interesting thing is you actually switch branches that are non-compressible originally into compressible branches. So about half of the branches on many benchmarks suddenly become 16-bit instructions, and that's a drive-by optimization. So since Jeff is already trying to get me off the stage here, just one conclusion, and one important one that I already hinted at before. So one thing that we really need to get right here is, besides having that feedback cycle being heavily fact-driven, on every instruction that we define now, we need to have the architects, the micro-architects, the software folks, performance, general algorithms, and tool chains in the room. And that's probably the most important takeaway for this year from my presentation. At that point, questions?
No, time is up. They're going to have to corner you. You've used up your Q&A time. So let's thank Philipp with applause.